Greetings from the Geoscience Research Institute. In today's presentation, we will reflect about our planet, considering data acquired from scientific investigation and interfacing it with the biblical perspective. So, is the Earth special? That's the question in the title of this presentation. The opinions on this differ. For example, in their book, The Privileged Planet, Gonzalez and Richards build a case for our planet not only being exquisitely fit to support life, but also fit to give us the best view of the universe, as if Earth were designed both for life and scientific discovery. Now, in another influential book, Ward and Brownlee refrain from using the concept of design and adopt a naturalistic model of Earth history. However, they also come to the conclusion that the Earth is probably to be considered special or rare, as the title of their book suggests, because they suggest that complex life is less pervasive in the universe than is commonly assumed. Finally, we can also consider a different point of view. In his book on planetary climates, Andrew Ingersoll concludes the book with a statement that presents yet another view which minimizes Earth's uniqueness. Earth seems to be a typical planet orbiting a typical star with a typical collection of raw materials that constitute the building blocks of life. There is no reason to believe we are alone. So, in a certain sense, we see that there is this spread of understandings and postures when it comes to the Earth as a planet that can host life. Is this something unique and special or not? Well, from a scientific perspective, a new way to more directly investigate the question of how special the Earth is has opened in the relatively recent past with the discovery of exoplanets. Exoplanets are planets outside the solar system. And although their existence had been postulated earlier, their detection only occurred starting from the 1990s. And there are several ways of detecting exoplanets, but two are the most common. With this animation, we can begin to look at the first one, which is known as the radial velocity method. Now, this detection method is based on the fact that if a planet orbiting a star is quite massive, the center of mass of the rotational system will be a little off the star, meaning that the star too will be wobbling around the center of mass. So as we observe this rotating system from the Earth in a radial direction, the electromagnetic waves coming from the star will be compressed or dilated as the star moves closer and farther, respectively, in its wobbly motion. So this shift in wavelength illustrated at the bottom of the animation will be periodical. And from it, one can estimate a minimum mass for the orbiting planet and also its distance from the star. Now, the second method, which we will see in this other animation, is the transit method. And this has been the most fruitful in the detection of exoplanets so far. And this is based on the fact that a planet transiting in front of a star will block some of the light that is received from an observer more or less aligned along the orbital plane. So that dip in luminosity, that drop that we see in the animation, will be greater if the planet's radius is larger because it will block more light. Also, the dip in luminosity will be observed periodically as the planet keeps revolving around the star, allowing to calculate the duration of a full revolution and the distance of the planet from the star. Now, one implication for both these detection methods, as we will see from the next slides, is that they are biased towards finding larger planets orbiting close to the star. But with the application of these and other methods of detection, we can see how the number of confirmed exoplanets has increased over time. Here we have several plots in a time series, and on the plot we have the duration of the orbital period or duration of the year in Earth days on the x-axis, and the mass of the planet in Earth masses on the y-axis. So notice that the scale is logarithmic in both axes. We can see that in the early years, detections were based mostly on the radial velocity method and included only very massive planets. But then, as we move through the years, we see that especially with data from the transit method, the catalog expanded to include planets with masses less than 10% of the Earth's mass. And with our most recent count in 2021, in excess of 4,300 confirmed exoplanets. Now, the plot does not show yet a real overlap with our planet Earth in terms of orbital period and mass. You can see that the confirmed exoplanets with similar or smaller mass are closer to their star, and the planets with similar or greater orbital period are more massive than the Earth. However, it is expected that with improvements in detection methods, this field will continue to be populated. Now, the discovery of exoplanets has allowed us to ask questions, many new questions, like, for example, what kind of stars have planets? How many stars do actually have planets? And how common are Earth-sized planets? Or is there a relationship between planet type and size and the distance from the star? Or what fractions of exoplanets are in the habitable zone? All these questions are being investigated, but one thing is already clear. The number and diversity of exoplanets is much larger than number and diversity of planets that we have so far known in our solar system. And as the catalog grew, it included also some unexpected surprises. For example, the occurrence of gas giants similar to our Jupiter, but orbiting very close to their star. Most importantly, the exoplanet census illustrates that the possible set of planetary types and conditions is vast, so that Earth-like conditions are not a default in the universe. Let's then review together some of the parameters that astrobiologists, who are the scientists who study the conditions necessary to sustain life in the cosmos, let's review the parameters that they are considering as important for a planet to be a good place for complex organisms like us to live on. Here is an example of a definition. You can see that in this definition, there are some key elements in the definition of habitability for a planet. First, we see the term mostly rock. So therefore, the planet should be a terrestrial planet, not a gaseous one. Also, a planet that can retain an atmosphere with certain specifications. Also, a planet that has availability of energy sources with certain specifications. And then a planet where liquid water is present. And finally, a planet that can keep these sets of parameters stable over time. Now, this is just one definition of habitability, but no matter the specifications chosen to define habitability, it is clear that habitability is not a function of one single variable, but lies at the intersection of multiple factors that have to coexist. So it's a much smaller subset of all the possible physical chemical conditions present in the cosmos. So let's then review more in detail some of the commonly recognized parameters from planetary habitability. Now, although there are possible sources of energy that could be used to sustain life originating from the interior of a planet, the most important source of energy is light from the star around which a planet is orbiting. it is not only crucial as a source of energy for living organisms, for example, on the Earth through the process of photosynthesis, but most crucially, it controls the possibility of having the right temperature for the availability of liquid water on the surface of the planet. Now, the temperature on the surface of a planet is a function of the distance of the planet from the star, among other parameters. So too close, and it will be too hot for liquid water to be a stable phase. Now, too far from the star, and we will reach the frost line, where water will turn into ice as the temperatures go below the freezing point. So this band or distance interval is called the Goldilocks zone or the habitable zone. And obviously, as you can see from the upper part of this illustration, the Earth is located within the habitable zone. Otherwise, we wouldn't have liquid water on its surface, right? Now, for a less massive star, like the one represented in the lower part of the figure, the habitable zone will be shifted closer to the star because of the smaller energy flux radiating from the star. Now, it turns out that not all stars are created equal. In our galaxy, stars less massive than the sun, like M stars at the top of this illustration, these stars are more abundant than sun-like G stars, which are represented at the bottom of the figure. So being less luminous, their habitable zone is located closer to the star. However, the M stars are also characterized by very high levels of emission of X-ray and ultraviolet radiation, actually up to hundreds times more intense radiation than what the Earth receives from the sun. Now, these energy flares and bombardment of high energy particles would affect the planets in the closely located habitable zone, making it difficult to preserve an atmosphere and also creating devastating effects for life. Moreover, at such close orbital range, a phenomenon which we will discuss later, which is called tidal locking, is also very likely to take place. And this would also decrease overall habitability. Therefore, even if there may be many planets in the habitable zone of a star, the kind of star and the type of radiation emitted are important parameters to consider for habitability. But why bothering so much about liquid water and even calling habitable the zone where temperatures are appropriate for the existence of liquid water on the surface of a planet? Well, we are all familiar with the fact that water is an important constituent of our bodies. What perhaps most of us do not realize is how intrinsic liquid water is to the life and metabolism of any living organism on Earth. As pointed out by Chaplin in an excellent review paper, liquid water is not a beat player in the theater of life. It's the headline act. Liquid water is essential for the folding, the structure, the stability, and the activity of proteins. It also plays a part in proton and in electron transfer reactions. And it plays a part in the structuring of DNA and in the recognition of specific DNA sequences by proteins. And it's also essential for the metabolic activity in the cell. So in other words, liquid water is essential for the biochemistry of life. No liquid water, no life. Let's now consider another important parameter for habitability, the atmosphere. Well, the atmosphere of a planet is important for life, not only for respiration, but also for temperature regulation by trapping some of the heat radiated from the planet. And it also controls climate. It provides a shield against some of the damaging solar radiation. And also it interacts with the hydrosphere and the lithosphere for the cycling of elements important for life. Now, when a planet is too small,
Ladies and gentlemen, I'm so sorry. We've got the wrong video up. This is running a lane which will be coming on at 10 o'clock. We will begin the proper video for Ben Clausen now. And we'll play that through to its entirety and as well as the Q&A afterwards. So we apologize for this error. And right now we have Ben Clausen coming up with the nature and the power of God.
It's an honor and a pleasure to be talking to you today about God's creation and his power that we see in nature and in human hearts. I'll be sharing with you online worldwide what I have shared in person to the ends of the earth. First, a bit of an introduction. I work in Loma Linda at the Geoscience Research Institute as part of the General Conference. The Institute has been tasked with studying God's second book of nature, but I should make it clear that it is not out to scientifically prove the Bible origin story correct. If that were the goal, one would end up disappointed, for God can do far beyond what human science can fathom. Our goal is to study nature from the perspective of God as its creator and to share the knowledge. One part is studying God's handiwork to see what he has to tell us about him and his power in nature. During the first 10 years at GRI, I did nuclear physics experiments, studying the very small things in nature, mainly at the Los Alamos lab, but at a number of other particle accelerators as well. Starting in about 2000, I realized that the Institute needed somebody studying geology more than physics. So for the last 20 years, I've been looking at geology issues. I started out by studying the granites here in Southern California, but the ones in Peru are similar. So since 2010, we have been looking at the granites in the foothills of the Andes. The question is, how fast do things happen in geology? Can you fit it all into a short time frame or not? The other part is sharing, organizing conferences that discuss science and religion, writing articles and books, maintaining a website, teaching classes about science and religion, and presenting lectures. There are now 4 scientists at the Institute: a biologist, a paleontologist, a geologist, and myself. They keep us traveling all the time except for the past year with the pandemic. So for example, in 2018, I gave science and religion lectures in Mexico, Zambia, Peru, Bolivia, Chicago, Nigeria, and Tanzania. And we did field research in Zambia, Peru, Hawaii, and Mexico, and lab research at UCLA and the University of Arizona. An example of the field work is leading a geology field trip for the Geological Society of America here in Southern California in 2016. 4 of us led a 3-day field trip over a weekend to look at the granites. I was in charge on Friday, then skipped the part on Sabbath and rejoined the group on Saturday night. As a result of being gone, some of the other geologists in the group asked me about my church. Here are some examples of the lab work. We used a scanning electron microscope at California State University Northridge to look at some of the little tiny zircon minerals that we collected in Peru. You've heard of cubic zirconium. This is about the same thing, except really tiny. They are about as big as the thickness of your hair. Then we used a mass spectrometer at University of Arizona to zap these little tiny zircon grains with a laser beam to count the uranium and lead atoms and figure out how old the rock is. We have gone to the Arizona lab a half dozen times. Here is one grain showing beam spots with ages from 403 to 538 million years. So what do you do with those hundreds of millions of years ages? In other words, What if the research seems to indicate a long time? This is the issue that I have to deal with just about every day in my research. But this brings me to my big question. How do we go about making Jesus, Christianity, and Adventism meaningful and appealing to people in the scientific community, people within our technological society, and young and well-educated Seventh-day Adventists? I have found a better way than arguing about science and religion issues. People seem to expect that maybe we can display signs and wonders. That was why they came to Jesus. But Jesus said it was an evil and adulterous generation that seeks after a sign. What was it that Jesus gave them instead? I would suggest that it was the kind of person that he was. Just as Abraham and his descendants were to be a blessing to the world, Jesus' message was to preach good tidings to the meek, bind up the brokenhearted, and proclaim liberty to the captives. One of my favorite books is The Desire of Ages, where it says that Jesus went among them as one who desired their good. That is the framework within which I study and teach. The resulting lectures that I give are on many science topics, and one on Christianity about aiding the development of science. Then I give some lectures specifically about Christianity. One that a professor at Andrews University has asked me to give several times is my own personal walk with Jesus. Another is faith in spite of uncertainty. How do I continue to have faith in the Bible, even though I may not necessarily be able to scientifically prove that it is correct? Another on how to deal with the issue of evil. If we serve a totally good and a totally loving God, why do we see all the bad stuff in nature and in the world? And another one I give is nature and the power of God. This last lecture is the one I will share here. Nature, from the universe down to the atom, by powers of 10. As we look at these next 40 slides, keep in mind that this is God's dominion and displays his power. We will start with a 1 meter square, about 3 feet across, of flowers on a bush on the mall at Loma Linda University. If you back away a little bit, your field of view will expand from 1 meter to 10 meters across. You can now see the Good Samaritan sculpture and the university library in the background. Another factor of 10 larger to 100 meters across shows an aerial view of the mall, the administration building, and the Centennial Complex in the background. Another factor of 10 to a kilometer across uses Google Earth to display the campus of Loma Linda University. Another factor of 10 to 10 kilometers includes all of Loma Linda. Then 100 kilometers for the Inland Empire. Then 1,000 kilometers for California, and so forth. Next, we see North America on a scale of 10,000 kilometers. The last time I gave this presentation was in Tanzania. It takes about 20 hours to fly from California at 800 kilometers per hour, or 500 miles an hour. That's a long, long ways from home. As we move out into space, we first encounter communication satellites orbiting at about 40,000 kilometers. The moon's orbit is at about 400,000 kilometers from Earth. It took Apollo 13 about 4 days to return at 5,000 kilometers per hour. But it only takes 1 second for light to arrive here from the moon. Further out at 10 million kilometers, we see Earth's orbit around the sun. A factor of 10 further includes Mars and Venus. Next, we see Jupiter and the asteroid belt. In this picture, you can see the sun in the middle of the solar system. It takes about 8 minutes for light from the sun to reach us here on Earth. The next order of magnitude includes the outer planets in the entire solar system. We then move out to interstellar space. NASA communication with Voyager 1 beyond our solar system takes 10 hours, even at the speed of light. Our solar system is now but a dot. The Oort cloud is so far away that it takes a year for light to travel that far. Distance is now measured in light years, a distance of more than 1 trillion kilometers. As we move farther and farther away and faster, we pass the nearest stars, Alpha Centauri at about 4 light years. Many of the stars seen with the naked eye are within about 50 light years and constitute the numberless stars that Abraham saw. Stars within a sphere of 1,000 light years across include those in the Big Dipper. The Orion spiral arm of the Milky Way is about 10,000 light years across. The Milky Way itself is about 100,000 light years across and contains 1 trillion stars and a black hole at the center. Within 1 million light years is the local group of satellite galaxies in the Magellanic Cloud. The Virgo cluster of galaxies within 10 million light years includes the Andromeda Galaxy. Galaxy clusters form the local supercluster out to 100 million light years, which form the largest structures within 1 billion light years, and the visible universe within 10 billion light years. In the Standard Model, this universe is explained by inflationary cosmology that began about 14 million years ago. As I look at the large sizes of the solar system and galaxy and universe, it reminds me of a verse in Isaiah. Lift up your eyes on high, and behold who has created these things, who brings out their host by number. He calls them all by name, by the greatness of his might, for he is strong in power, and not one faileth. Then I read in the Desire of Ages that God is in active communication with every part of his creation. How is he in active communication with the entire universe that takes billions of lights for light signals to travel from one side to the other? To give you a picture, let's talk about the story in Daniel chapter 9. We usually think about the 70-week prophecy near the end of this chapter. But before that, Daniel is praying for his people. It takes about 3 minutes to read the prayer. At the end of the prayer, an angel comes to Daniel. The angel says, "At the beginning of your prayer, I was commissioned by God to come to you." So it appears to take 3 minutes for the angel to come from heaven to Daniel. Now, how long does it take for light to reach us from the sun? It takes about 8 minutes. So either heaven is closer to us than the sun, or the angel traveled faster than the speed of light, or maybe there's some kind of a fourth dimension. In any case, it suggests that maybe there is a lot out there that's far beyond our understanding, that God's dominion is far beyond what we know. But God is also interested in the small. Jesus said that the very hairs of our head are numbered. These small sizes are where most of the range of light wavelengths are important. So we start back with the 1 meter square containing flowers in the Loma Linda University Mall. Let's say that one of these flowers has a bee on it. Looking closely, we see the bee's head. Closer, at 1 millimeter or 1,000 microns in size, we can see the eye of the bee with maybe some pollen on it. Pollen grains at less than 100 microns across are about the thickness of a human hair. A bacterium cell is less than 10 microns across. At 1 micron, we see a bacteria with viruses on it. A virus is less than 1/10 of a micron across, the same wavelength as visible light. Inside the virus is the DNA helix, visible with an electron microscope. The DNA is made up of molecular units. The molecular units are made up of atoms, each of which has an electron cloud. Inside the atomic electron cloud is mostly empty space. These sizes are the wavelength of gamma rays. Down to less than 1/1,000,000th of a meter, we can see the atomic nucleus, which contains protons and neutrons held together by the strong nuclear force. And even these protons contain smaller up and down quarks. With quarks, we've reached the detection limit at the small size, along with the force carriers. God's universe includes the very small as well as the very large. A few years ago, my dad asked me about a statement he had read. There are more molecules in a water drop than there are people on the earth. He asked me, is that really true? After a few calculations, I said, not only is that true, but there are more molecules in a drop of water than there are hairs on the heads of all the people on the earth. God keeps track of a lot of hair, but also a lot of molecules and atoms as well. As a nuclear physicist, I am reminded of God's power at the very small size inside the atom. The atom doesn't weigh very much, it doesn't have very much mass, m. But if you take that mass and multiply it by the speed of light, c, and then multiply it by the speed of light again, you can get a lot of energy out of it. E equals mc squared. A little bit of mass gives a lot of energy. So God's energy and power can be seen in the atom as well as the universe. Now I would like to talk about examples from the Bible, describing God's power in nature, how we have too small a picture of God, the best example of God's power, and what we as Christians and Seventh-day Adventists have to share about God's power. So, some examples. In Isaiah 55, God says, my thoughts are not your thoughts. 1 Corinthians says, eye has not seen nor ear heard, neither has entered into the heart of man the things which God has prepared for them that love him. And Romans says, God's eternal power and Godhead are clearly seen from the creation. In Job 38, in the next few chapters, we find God talking about nature. As you read through Job, you find that he had a lot of questions for God. He demanded to talk to him. But when God finally responded, did he answer Job's questions? No. He just asked questions about nature. Chapter after chapter, where God asks him questions to demonstrate that Job really doesn't know much about nature at all. In Job's response in the final chapter, he says, I know that you can do everything, and that no thought can be withheld from you. I uttered what I didn't understand, things too wonderful for me, which I knew not. Similarly, Jesus told the Sadducees that they had too small a picture of God. He said, ye do err, not knowing the scriptures nor the power of God. We also often have much too small a picture of how great God is. When I was a kid in Pathfinders, I did progressive classwork. One year, we were supposed to memorize the 10 Commandments. I'm not very good at memorizing and thought that was an awful lot of verses to memorize. I especially wondered why the second commandment was so long. It would have been a lot simpler if God had just made a short command, don't worship idols. I could have memorized it a lot easier instead of two rather long commands. Since then, I have realized that the second commandment is saying something different from the first. The first one says, "Thou shalt have no other gods before me." But the second one says, even if you worship the true God, don't worship some human representation of how great that God is. It's easy to have too small a picture of what God is like. In Deuteronomy, God specifically said, "You haven't seen what I look like, so don't try to make a representation of what I'm like." The danger is, once you start looking at that representation, you think that that is all there is to God, and you forget how great He is. Today, we may not have the problem so much of worshiping idols of wood and stone, but we probably still have the problem of having too small a picture of how great God is. When I was a kid, my older brother gave me the book, "Your God is Too Small." The first half of the book has a number of chapters with example of how our picture of God is too small. One particular one caught my attention, entitled "The Grand Old Man." God has been around a very long time, and Jesus taught fishermen and farmers, so He must not be very up to date. Would He be able to run a computer, or a nuclear facility, or fly a jet aircraft? Your first thought is, you just can't picture that. But of course, He would understand how to do that, and so much more. Now let's look at God's power in a different area. Elijah saw the power of God in nature on Mount Carmel, fire from heaven that consumed the sacrifice and the altar stones and the water. But then he fled from Jezebel to Mount Horeb. There he also saw what seemed to be God's power in nature, in the wind, the earthquake, and the fire. But you notice that 1 Kings 19 says that God was not in any of those. Where was God instead? Apparently in the still small voice. This suggests to me that yes, we see God's power in nature, but there may be even a more important place where we see God's power, in that still small voice. So what is that power in the still small voice? I would suggest that it's a power that can turn the world upside down. In Romans 1, it says it's the gospel of Christ, the power of God to salvation. In 1 Timothy, it says, in the last days, men will have a form of godliness, but deny the power. From such turn away. So, there can be a power that turns the world upside down, but there can also be a form of godliness that lacks that power. In Colossians and in John chapter 1, we find that that power was fully manifested in Jesus Christ. The Word was made flesh and dwelt among us, and we beheld His glory. The glory is of the only begotten of the Father, full of grace and truth. And where does God's power fit in? As many as received Him, to them gave He power to become the sons of God. So this is the real power, to become sons and daughters of God. How do we share that message? That has been my question for many years as I work in the scientific community. How do I share that message with my science colleagues? Again, back to the desire of ages that I find so helpful. Though rich, learned, and honored, Nicodemus had been strangely attracted by the humble Nazarene. In another place, it says, men of the highest education in the arts and sciences have learned precious lessons from Christians in humble life, who were designated by the world as unlearned. And elsewhere, unprejudiced thinkers received his teaching and found that it tested their wisdom. The most highly educated were charmed with his words. I give another lecture about how we share our message. This slide is somewhat of an outline. Again, many insights from the desire of ages. She seems to suggest that it's not as much facts as a life to be shared. Several places she talks about sharing quietly and gently. At times, Jesus encouraged people not to speak at all. One example is about Paul as he talked to the philosophers in Athens. He felt he had been unsuccessful there, so at Corinth, he decided to use a different method, Christ only instead of argument. In other places, she suggests restraining without obscuring truth and how to meet opposition. I have many examples in working with my science colleagues of how I go about sharing. Here is one example. Almost 15 years ago, I attended a geology conference in South Africa. When I flew into Cape Town, I had to wait with the geology group for transportation to the conference venue. While waiting, I saw a strange man in the airport. He had long braided hair, a necklace of small skulls, and a hat with horns. Then I noticed that he was coming toward our group. He was one of the geologists attending our conference. In the van, I visited with him a bit. At the conference, we went out to eat at restaurants together several times. I didn't really try to talk to him about Christianity, but it came up because I told him about the university where I teach. We talked a bit about creation, and I suggested that life coming from non-life seemed pretty hard to have happen. He said, "Well, we just haven't figured that out yet." I didn't argue. We parted as friends. A couple years later, I attended some geology meetings in Portland, Oregon. As I was walking down a hall to a different session of talks, I saw him coming down the hall from the other direction. Over all of the other geologists, he called out to me, "You're that Christian, aren't you?" I smiled and said yes, and went on to my meeting. The next morning, I saw him and his wife eating at a local restaurant and went over to say hello. He said, you're a Mormon, aren't you?" I said, "No, I'm a Seventh-day Adventist." Then he asked what we believed. I've been asked this question many times as I worked at science labs. Often, I would just give a list of doctrines, but this time I decided to give a different answer. I said that I work at Loma Linda University, where we have the goal of continuing the teaching and healing ministry of Jesus Christ in trying to make the world a better place. He liked that. I was on a week field trip with him again a couple years later. The first night, he again asked me about being a Christian. We had some additional friendly visits. I didn't convert him to Adventism. That isn't even my place to do. But we are friends, and he has a positive impression about what a Christian can be like. Not obnoxious, but someone he would like to spend time with. So, what do I have to share? I share my life story, the story of a believer, not because of signs and wonders, but because of God's picture of how to live. I grew up as a preacher's kid, studying both science and the Bible. The first article I wrote in academy was on evolution and creation. During college, I spent a year in Africa teaching as a student missionary. My geology master's degree at Loma Linda helped me realize how little we know. So I switched to physics at University of Colorado that seemed to provide much more certainty. In my dissertation acknowledgments, I thank God for the fascinating world he created to study. Now I am studying geology again, looking for coherence between God's two books. I find it useful to get out there and mingle with the people in the scientific community, to win people more than arguments, and to offer a Christ-like God, something more than pure naturalism, a caring God and community, and a better picture of what God is like, a God who is both totally good and fully powerful. Our God is a good God, even though we may see evil around us. I give a talk about dealing with the evil. Although we can't explain it, we find clues about evil within the context of creation and origins. God made a good creation, so evil is not God's fault. Humanity fell because God allowed free will and the opportunity to truly love. God sent a flood, showing how he responds to evil with justice and mercy. God became incarnate, so the Creator feels the evil along with us. God limits it in time, so evil is only for a moment. And God promises a future recreation where evil will be forever eradicated. And our God is a powerful God, for with God all things are possible. Our limited human understanding may result in seeming paradoxes, for God can be omniscient while we still have free will. For Jesus is both fully divine and fully human. God has 1,000 ways to do things of which we know nothing. So, we don't know how God accomplished everything in Genesis 1-11. 10 years ago, I organized some science and religion meetings in the Canadian Rockies. There were a lot of science talks and some philosophy talks. Afterwards, one of the attendees sent me an email where she said, "I didn't really understand all the details of the science, but I'm a believer, and here's a video clip that has meant a lot to me in understanding the greatness of God here in this world, and it leads me to see God in nature and to believe in him." Doing a Google search for YouTube creation calls gives many versions of this beautiful 5 to 10 minute video clip. Try it and see. You'll enjoy it a lot. For a benediction, I would like to give you this charge. As we see God's power in nature, may it remind us of the power of God we can experience in our own lives to become his children. Not power to argue for a particular viewpoint, whether in science or theology, but power to care about those who touch our lives. Not a form of godliness, but the power of the gospel of Jesus Christ.
Very well.
So I'm